Hello everyone, hope you are doing very well. Today, as you all know, that we are going to cover the theory part 6 of the chapter Haloalkanes and Haloarenes. So, let's begin our today's topic. NCERT chapter 6 Haloalkanes and Haloarenes, theory part 6, and today we are going to focus on the NCERT section 6.6. This is disclaimer. Objective. So today's lecture objective, after attending this lecture, you will be able to describe the reactions that involved in the preparation of haloalkanes and haloarenes, and also you will understand the various reactions that they undergo. Also, you can correlate the structures of haloalkanes and the haloarenes with various types of reactions, right? So let's see. Today, we are going to cover the topics according to the NCERT. The first section is 6.6 Physical Properties, in which we also cover two in-text questions. That we will also practice two in-text question number 6.4 and the 6.6. So, let's start with the topic, section 6.6 Physical Properties. And in the physical properties, because we are studying in the chapter Haloalkanes and Haloarenes, let's see the physical properties of haloalkanes first. So, haloalkanes means halogen and the alkane, okay? Alkyl halide you can also say. So, the color, if you talk about the color of haloalkanes, the pure alkyl halides without any, you can say, impurity, they are colorless. They don't show any kind of color. Okay, that's why we are using here pure. So, pure alkyl halides are colorless. They don't show any color. They don't exhibit any kind of color. Bromides and especially iodides develop color when they exposed to light due to the decomposition. So, when you do the decomposition of bromides and especially the iodides, they might develop color when they are exposed to the light. Okay. Smell. Now, if you talk about the physical property, that is smell of the haloalkanes, many volatile halogen compounds have sweet kind of smell. Okay, so sweet smell. Many volatile halogen compounds. So the halogen compounds that have volatility, or you can say that are volatile in the nature, that can easily convert to the vapors, they have sweet smell. Okay. If you talk about the major physical property, that is melting and the boiling points of haloalkanes, let's understand that first of all, methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethanes are gases at room temperature. So at the normal temperature, when you are not increasing any temperature, then at the room temperature, these compounds like methyl chloride, where methyl, that means methyl group, methyl alkyl group is attaching with the chlorine halogen, methyl bromide, where halogen is bromine, and ethyl chloride, where halogen is chlorine, but the carbon chain is of 2 carbon, ethyl, and some chlorofluoromethanes. Now here there is two kind of halogens present, chloro and fluoro, that means chlorine and fluorine. So in these kind of compounds, they are actually gases in the, they are in gaseous form at the room temperature. Okay. Higher members, like if the higher atomic, or you can say if the higher member of the halogen group is forming any kind of haloalkanes, then those are either liquids or solids. Okay, so in the liquid state or in the solid state. So higher members are either in the liquid state or they are in the solid state. That means they are having higher melting points. Okay, so basically, if we compare the haloalkanes melting point with their corresponding alkanes, okay, where no halogen is present, comparatively, the haloalkanes are going to have greater melting point than their corresponding alkanes, right? The second thing is, why is it so? It is because of the stronger intermolecular forces. That means stronger dipole-dipole interaction that is present in the haloalkanes, in the carbon-halogen bond, and there are stronger dipole-dipole interactions and the van der Waals forces, which is absent in the alkanes if you compare with the alkanes, right? And this is the reason that haloalkanes have greater melting point comparative to their corresponding alkanes. And also, if we talk about the haloalkanes, like where you are changing the halogen with the alkyl group, so higher members, you can say higher members are having greater melting point than the starting members, initial members like fluorine and chlorine. Okay, so the order will be like alkyl iodide will be having the higher melting point, then the alkyl bromide, then alkyl chloride, and then the least will be for the alkyl fluoride. So melting point increases with the increase in the halogen atomic weight. That's why we are saying that higher members are either liquids or in the solid state. If we talk about the boiling points, there is high boiling point shown by the haloalkanes, and the reason behind this is that haloalkanes are polar molecule. The similar kind of reason that the boiling point of haloalkanes, if you compare to their corresponding alkanes, is greater. Why? Due to the same reason that the carbon-halogen bond here is the polar, and due to this polar nature present in the haloalkanes, the bond is held by stronger dipole-dipole interactions or van der Waals forces, which will cause the increase in the boiling points. Okay, so polar carbon-halogen bond, due to which there is greater, also there is greater molecular mass. If you increase with the halogens, like down the group, as the molecular mass increases, the boiling point will increase. And also you can compare it with the corresponding alkanes. Alkanes don't have this polarizing nature. Along with that, alkanes comparatively have lesser molecular mass than the haloalkanes. This is also a reason that the haloalkanes having higher boiling points. If we talk about the chain length, so basically if there is a greater molecular size or the greater chain length, then it will corresponding to the greater surface area. That means greater boiling point. Okay, higher boiling point. But if we are having branch chains where branches are made up and then their boiling point will decrease, then their corresponding straight chain isomers. Okay, because there is decrease in the surface area and the branched chain isomers of the haloalkanes cases. Okay, and the reason for the high boiling points, as we said, that it is polar molecules. Okay, and due to this increased or stronger dipole-dipole interactions, there is the higher boiling points observed for the haloalkanes. The intermolecular force of attraction, which is dipole-dipole and the van der Waals, they are stronger than in the parent hydrocarbon. So in the parent hydrocarbon, there is no dipole-dipole interaction present, which is actually present in the haloalkanes, which is stronger attraction. So due to this stronger intermolecular force of attraction, the boiling point of the haloalkanes comparatively will be higher from their corresponding alkanes or hydrocarbons molecules. Okay. So we are talking about the melting and the boiling point of the haloalkanes. Trend. If we notice the trend, let's observe the trend number 1, where the alkyl group is same, but the halogen group is different. So we are changing the halogen group, but the alkyl group we are remaining, or we are putting the same. So for same alkyl group, let's say that is R. Either it can be methyl, ethyl, propyl, any alkyl group you can take, but you should have take the same alkyl group which is bonding with different halogens. So if this is the case, then the boiling point will increase with the atomic mass of the halogen. Okay, as the greater atomic mass of halogen will be attached with the alkyl group, the same alkyl group, so the boiling point will increase in that order. So trend 1 will be that alkyl iodide having the greater boiling point than the alkyl bromide, and alkyl bromide will have greater boiling point than alkyl chloride. Alkyl chloride have greater boiling point than alkyl fluoride, where R group is same, but we are changing the halogens, right? So as the atomic mass of the halogen is increasing, the boiling point is increasing in that way down the group, right? Due to increasing van der Waals forces with the increased size and the mass of halogen atom. Now why this is the trend we have observed? Because the van der Waals forces is increasing as the halogen is changing, the carbon halogen bond is changing, right? The polarity is changing. So there is the stronger polar or increasing van der Waals forces between the carbon and the halogens, or you can say among the haloalkanes, with increasing size. Along with that, the size is also increasing and the mass of halogen atom is also increasing, due to which the boiling point is also increasing. This is the graph you can see. This is figure 6.1. Comparison of boiling points of some alkyl halides. So we have given 3 alkyl halides: CH3X, CH3CH2X, and CH3CH2CH2X. That means methyl halide, ethyl halide, and propyl halide. So we are now comparing the melting and you can say now we are comparing the boiling points of alkyl halides, where we are changing the alkyl also and we are changing the halide also. How? This red, blue, and yellow are corresponding to chloride, bromide, and iodide respectively. Okay, so the red graph is for the chloride one, like methyl chloride graph. Okay, and then bromide is for blue, so methyl bromide will be this for this this blue graph will be for methyl bromide, and yellow one is the iodide, so this yellow graph here is for the methyl iodide. Okay, so you can see that if you compare between these three, the red graph in all the three like alkyl halides is the lesser one, and the yellow graph is the higher one, right? Comparatively in between the molecules, not in between the halides, but in between the molecules. If we compare, their red graph is at the lesser range and the yellow graph is at the greater range. It covers the greater boiling point range, right? The yellow one. So as I said that if you don't change the alkyl group, if you take the alkyl group as same and change just halide group, that is chloride, bromide, and iodide, so as the atomic mass of the halogen increase, the boiling point will also increase. You can see this, right? Red is showing the smallest boiling point around between 200 and 300, and blue one is showing the greater boiling point than the red one, that is chlorides, methyl chloride. So blue one is for methyl bromide. Methyl bromide are having higher boiling point than the methyl chloride, and similarly methyl iodide is having more higher or more greater boiling point than the methyl bromide and methyl chloride, right? Similarly, in each molecule you can observe that the red is ranging at the lower range, red is at the lower range of the boiling point, and yellow graph is at the greater range of the boiling point, right? So this is the similar trend, that if you don't change the alkyl group and only change the halogens that are attaching with the alkyl group, then as the atomic mass of the halogen is increased, its boiling point will also increase. You can observe this in the each molecule graph. Now if we observe in like a different molecule, so as you are increasing the size of the molecule by adding more and more carbons into it, like adding more chains. Okay, so in the first molecule we have only one carbon, in the second molecule we have two carbons, and in the third molecule we have three carbons, right? So propyl halide. So as the number of chain, as the length of the chain is increasing, that means as the size and the mass of the molecular mass of our molecule is increasing, its boiling point is also increasing, right? Like methyl halide, all the graph, if you see the highest graph for methyl iodide, it is comparatively at the lower range of boiling point. Then for the propyl iodide, it is present at the higher range of boiling point, right? So if you compare among the molecules, as the length of the chain is increasing, the surface area is increasing, the molecular mass is increasing, along with that the boiling point of the alkyl halide is also increasing. So this graph is actually the comparison of boiling points of some alkyl halides. Okay. Let's see the trend 2. for the melting and the boiling points. Okay, so trend 2 is among the isomeric haloalkanes. Okay, now we are talking about the isomers of haloalkanes. Like molecular formula will be same, but structural difference will be there. For the isomeric haloalkanes, the boiling point will decrease with the increase in the branching. Okay, so as the branching is increased in the molecule, in the chain, if we are increasing the branching, then that branching means if you are putting more and more substituents into your chain and decreasing the size of the chain, then your boiling point will also decrease. Why? What is the reason? The branching of the chain decreases the surface area of the molecule, which in turn decreases the magnitude of van der Waals forces. Right? So, if the surface area due to the branching decreases, this will cause the decrease in the magnitude of van der Waals forces shown by the haloalkanes. Right? And this is the reason why their boiling points will also decrease. Right? So, straight chain isomers is having lesser surface area than the branched chain isomers. Right? Okay. Straight chain isomers is having greater surface area than the branch chain isomers, due to which comparatively straight chain will be having the greater surface area, will be having the greater magnitude of van der Waals forces and greater boiling point comparative to the branch chain isomeric haloalkanes. For example, if you take the molecule whose formula is C4H9Br, 1 bromine, 4 carbon, 9 hydrogen. How can you arrange this molecular formula like into different structures? So let's see. So this C4H9Br, the first method is you can put all the carbons in a single straight chain. Along with that, at the very end or at the very first carbon, you put the bromine. Right? The boiling point in the Kelvin for this molecule, which is actually bromobutane, is 375 Kelvin. Second type, or you can say second way you can draw the structure of the C4H9Br molecule is CH3, CH2, CH, CH3, and at the second position you put this bromine. So you are branching your chain. Okay, rather than the straight chain by putting the bromine at the first carbon, you are branching the chain by putting the bromine at the second carbon. Okay, so you are putting the bromine at the second carbon, so there is a substituent present in this straight chain of the 4 carbons. So this is comparative to this first structure. The second structure is a branched isomer, right? So its boiling point will decrease due to the increase in the branching. So 375 will be decreased to 364 Kelvin. Now if you do the more branching, like you can arrange the C4H9 bromine molecular formula as this in the structurally. So you are putting 3 carbons in a single chain, and at the second carbon you are putting 2 substituents as a branch, which is one group of methyl and the other is bromine. Right? So you are selecting this straight chain as your parent chain, and at the second position there is 2 substituent present, CH3 and bromine. So there is increase in the branch. The first molecule have no branch, the second molecule have 1 branch, the third molecule have 2 branches. Right? So its boiling point will also decrease. So from 364 it will go to 346 Kelvin. So this is how the change in the branch or increase in the branch will decrease the boiling point of the molecule. Okay. Now let's see the physical properties of haloarenes. First of all, melting and the boiling points. Boiling points of isomeric dihalobenzenes are very nearly the same. Dihalobenzene means benzene is attaching with 2 halogens, like the molecule is having 2 halogens into it. So the boiling point of isomeric dihalobenzenes are very nearly the same. Okay, so basically the molecule which are having benzene ring attaching with 2 halogens and if you arrange them isomerically in different structures, their boiling points are very nearly the same, but they are different, but they are nearly the same. Melting points of para-isomers are significantly higher than their ortho and the meta-isomers. If you talk about the melting point especially, the para-isomer are having the greater melting point than their ortho and the meta-isomer due to the better packing in the solid state that we will see. So the reason behind this increase of melting point of para-isomer is that para-isomer is more symmetrical. If you see the structure of dihalobenzene, where one halogen is at the very first carbon and the other carbon and the just alternate carbon of the first carbon will be having the other halogen attaching with it. So it is a symmetrical structure. So para-isomer, okay, this is a para-isomer. Para-isomer is more symmetrical, and due to which it will fits better into the crystal lattice. So due to this better packing in the solid state and the crystal lattice, the melting point of para-isomer will increase. So it is significantly higher than their ortho and meta-isomers. Remember, we are talking about the melting points. This is not the case in the boiling points. Okay, so basically, if we compare in general, with the increase in the size and the mass of halogen, the boiling point of haloarenes increases, right? That means the iodobenzene will be having the highest boiling point and the fluorobenzene will be having the lowest boiling point, okay? Dihalobenzene boiling point are quite similar, as I said. Why? Because order can vary based on the molecular symmetry and packing. Okay, they are nearly the same, but still there is order, there is difference, and that difference can be due to the molecular symmetry and their packing. Okay, so if you talk about the orthoisomers of the dihalobenzenes, their boiling point are comparatively greater than the para and the meta-isomers. Why? Because there is closer proximity of the halogens, which is affecting the intermolecular interactions, due to which the boiling point increase for the orthoisomeric dihalogen benzenes. Okay, so melting points of para-isomers are significantly higher. The reason we have seen, because it is more symmetrical and it fits better into the solid state, into crystal lattice. They have strong intermolecular forces. They require more energy to melt, so their melting point are higher. The example is molecule with the molecular formula C6H4Cl2. So if you write the C6H4Cl2 in different way by changing the positions of one chlorine with respect to the other, you can draw these three diagrams or these three structures for this given molecular formula. First is where one chlorine is, this chlorine is present at the ortho position with respect to the first chlorine. Okay, so the ortho isomer will be having the greater boiling point than the meta and para, right? So its boiling point will be the highest. You can see 453 and others are having 446, 448, right? Because the second structure, you can see the chlorine is present at the meta position with respect to the first chlorine, and in the third structure the chlorine is present at the para position with respect to the first chlorine. So para isomer will be having significantly higher melting point than the ortho and the meta, right? So para will be having the highest melting point, 323. You can compare 249, 256. Both are lesser magnitude of melting point than the this diachlorobenzene, right? So this is the trend, and this is the structure of this molecular formulas. This molecular formula have these three structures and their respective boiling point and a melting point, due with the help of which you can understand the points which I had told you, that the boiling point of the orthoisomer will be greater due to the closer proximity, okay, which is going to affect the intermolecular interactions. Okay, so and the para isomer will be having the highest melting point, 323, and the orthoisomer will be having the highest boiling point, 453, right? Other structures have their boiling point and melting point lesser value comparative to the ortho and the para in case of like boiling and the melting point respectively. Now, the physical properties of haloalkanes and haloarenes. Comparatively, or you can say combinedly, if you talk about the physical property of haloalkanes and haloarenes, both, let's first talk about the density. Density is a measure of how much mass is contained within a given volume. Okay, so within a given volume, how much mass is actually present, how much mass this volume is containing, this is what density measured. So density you can define in the formula as mass upon volume. With the greater mass, the density will increase. With the lesser volume, the density will increase. But with the greater volume, the density will decrease. Bromo, iodo and polychloro derivatives of hydrocarbons are denser than the water. So if you compare with the water, the bromo, iodo and polychloro derivatives of the hydrocarbons are more denser. Why? What are the factors that affect the density? First of all, increase with the increase in the number of carbon atoms. The density increase with the increase of the number of carbon atoms in the haloalkanes and the haloarenes. Like so simple explanation that as the number of carbon atoms increase, the chain length increase, the mass is increasing. Okay, so the mass is increasing means density will increase. So density will increase with the increase in number of carbon atoms. Also, density will increase with the increase in number of halogen atoms. So if you talk about the halogen atoms, if you attach different halogens with the haloalkane and the haloarene, or you can say alkyl and aryl group, right? As the number of halogen atom you will increase in the alkyl group and the aryl group, there will be increase in the density of the molecule. Okay, because there is greater number of halogen atom, greater mass is attaching with the molecule, with your alkyl or aryl group, right? This is going to cause you increase mass, that means increase density. So density will increase with increase in the number of halogen atoms. Also, density will increase with atomic mass of halogen atoms. So if you attach different halogen atoms, not in number but in way, like you are attaching bromine, iodine, fluorine, chlorine, right? So as you are attaching the higher members of the halogen group within your alkyl or aryl structure, there will be increase in the density. Okay, so density will increase with atomic mass of halogen atom. As the atomic mass of halogen atom increase present in our haloalkane and haloarenes, the density of the molecule will also increase. Physical properties of haloalkanes. So we are talking about density, right? Let's see the table 6.3. Table 6.3, which is showing the density of some haloalkanes. This is the table, and in the table we have the compound and their density in gram per milliliter. You can see we have the first compound as NC3H7Cl, that means straight chain having chlorine at the very end. Then we have NC3H7 bromine, and then we have NC3H7 iodine. So in the 1, 2nd and 3rd compound, the alkyl group is same, but only we are changing the halogen. From the lower atomic mass to the higher members, we are attaching with our alkyl group with the same alkyl. So its density is affecting. It is increasing. So as the halogen atomic mass is increasing, the density is increasing from 0.89 to 1.337 or 335 to 1.747. Now if you see the compound 4th, that is CH2Cl2, the compound 5th CHCl3, and the compound 6th CCl4. Here what we are doing, we are taking only single carbon, but we are increasing the number of same halogen that is attached to the molecule, right? So firstly we are taking 2 chlorines attaching with the methyl group. then we are taking 3 chlorines attaching with methyl group, then we are attaching 4 chlorines, right? So as the number of halogen atoms increases, the density will also increase from 1.336 to 1.489 to 1.595. So this is the table showing the density of some haloalkanes and how they differ. In the molecules 1 to 3, in these first 3 molecules, with the increase in the mass of halogen atom from chlorine, bromine to iodine, the density is increasing from 0.89 to 1.747, right? And in the molecule 4 to 6, last 3 molecules given in the compound column, with the increase in the number of halogen atom, the density is also increasing, because you are increasing the number of halogen atom attaching with your molecule. The density is also increasing from 1.336 to 1.595, right? So this is what this table is predicting. Let's talk about the solubility. Haloalkanes are only very slightly soluble in the water. Okay. So why it is so? Haloalkanes are not very good soluble in the water. Haloalkanes are very slightly soluble in the water. The reason is that energy that is needed to break the strong hydrogen bonds in the water and the attractions within the haloalkanes. Okay, so the hydrogen bonds are in the water molecule are held by strong hydrogen bonds, right? So water molecules are held by strong hydrogen bonds. So water molecules are having stronger hydrogen bonds and you need to break them. And within the haloalkanes, the attractions are also stronger, right? So both the when haloalkanes are added to the water, they need to break these hydrogen bonds in the water and the attractions within a haloalkanes, right? So there are strong hydrogen bonds present in the water. Okay, so water molecules are held together by the strong hydrogen bonds, and to dissolve the haloalkanes in the water, these hydrogen or these strong hydrogen bonds must be broken, right? The new attractions that are going to form between the haloalkane molecules and the water molecules are much weaker than comparative to these hydrogen bonds. Okay, so the hydrogen bonds in water molecule are stronger, and the molecule or the attraction that will form between the water molecule and the haloalkanes after the dissolving or after the solubing the haloalkanes in the water, that attractions will be comparatively weaker. Okay, so this weak interaction does not compensate for the energy that is required to break the hydrogen bonds, due to which only a small amount of haloalkane is dissolved in water. So that's why we are writing that haloalkanes are only very slightly soluble in the water. New attractions between the haloalkanes and the water that are going to form are too weak to release the enough energy to compensate these stronger hydrogen bonds present in the water, due to which very haloalkanes will show very little or slightly lower solubility in the water. Haloalkanes dissolves in the organic solvents. So we are saying that haloalkanes are dissolving in the organic solvent. Okay, why is it so? The reason is that new intermolecular attractions that are formed between haloalkanes and organic solvent, they are similar in the strength to the attraction that is being broken. Okay, so when both the haloalkanes and the organic solvents, they are generally non-polar or they are either weakly polar. Okay, so when haloalkanes are added to the organic solvents, similar types of the intermolecular forces like van der Waals forces, they are existing between the molecules, right? So the energy that is needed to break the attractions between the haloalkane molecules and the attractions within the solvent, within the organic solvent, they are same, they are similar in the energy, or they are similar to the energy that is given out when new attractions will form. So, due to this compatibility, it will lead to good solubility of the haloalkanes in the organic solvents. Okay, so this is the main reason that why haloalkanes are dissolved or good dissolving in the organic solvents, because the attractions between the organic solvents and the new attractions that are going to form between the haloalkanes and the organic solvents, they are similar. Okay, and also the haloalkanes are very slightly soluble in the water, okay, due to the stronger hydrogen bonds in the water which can't be broken, and the new attraction that will form between the haloalkanes and the water molecules, they are weaker comparatively, so they are too weak to release enough energy to compensate, due to which haloalkanes are very slightly soluble in the water. Okay, let's do an in-text question. In-text question 6.4. Question is, among the isomeric alkanes of molecular formula C5H12, identify the one that on photochemical chlorination yields a single monochloride, 3 isomeric monochlorides, 4 isomeric monochlorides. So, among the isomeric alkanes of this molecular formula C5H12, you have to identify the one that on the photochemical chlorination will yield a single monochloride, 3 isomeric monochlorides and 4 isomeric monochlorides. Okay, so you have given some time, try to solve this question and then we will see the answer. Okay, let's see. So for this question, first of all, you have to find that to have a single monochloride, there should be only one type of hydrogen atom should be present in the given molecular formula in the isomer of alkane of molecular formula C5H12, right? For having single monochloride, the formula or the molecular formula given C5H12, this isomer of alkane should have only one type of hydrogen atom to be replaced by the chlorine. So replacement of any hydrogen atom leads to the formation of same product, and that isomer is neopentane. If you see, the structure of neopentane is this, where every hydrogen atom is only similar type of hydrogen atoms is present in this formula or in this structure, right? Similar type of hydrogen is present in this structure, due to which any hydrogen if you remove or any hydrogen if you replace with the chlorine, that will going to yield you same product, right? So the isomer that will going to give you a single monochloride is the neopentane, having the molecular formula C5H12. Now, to have 3 isomeric monochlorides, which is our second part, the isomer of alkane of the molecular formula C5H12 should contain 3 different type of hydrogen atoms. Okay, so that with each replacement of hydrogen atom with the chlorine, they will yield different 3 isomeric monochlorides. And this isomer is N-pentane. So there are 3 types of hydrogen atoms which is labeled as A, B and C, which is present in N-pentane. And this is this CH3, CH2, 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 CH3. Okay, the A type of hydrogen is present at the very center, the B type of present at the second carbons, okay, and the C type of hydrogen is present at the first carbons or terminal carbons. This is N-pentane, containing 3 different type of hydrogen atoms. Replacing these 3 type of hydrogen atoms can form or can give you 3 isomeric monochlorides. Now, for the third part, to have 4 isomeric monochlorides, the isomer of alkane of the molecular formula C5H12 should contain 4 different type of hydrogen atoms, right? So for this molecular formula, C5H12 and to have 4 isomeric monochlorides, the isomer of this molecular formula should have 4 different type of hydrogen atoms, so that with each replacement of one hydrogen atom with the chlorine, you will get 4 isomeric monochlorides, and that isomer is 2-methyl butane. So there are 4 types of hydrogen atoms that are labeled as A, B, C and D in 2-methyl butane. So let's see the structure. This is the isopentane or 2-methyl butane, where at the second position there is methyl, and in the parent chain we have 4 carbons. And there are 4 different types of hydrogen present. A, which is present as at the very CH3 at the very first carbon, B at the very second carbon, C at the very third carbon, and D at the very fourth carbon. Okay, and after replacing these 4 kinds of different hydrogen atom with the chlorine, you will get 4 different isomeric monochlorides of the molecular formula C5H12. Let's solve the next in-text question, 6.6. Question is, arrange each set of compounds in order of increasing boiling points. First is that bromoethane, bromofoam, chloromethane and diabromomethane. Second, 1-chloropropane, isopropyl chloride and 1-chlorobutane. So for these 2 parts, you have to arrange these set of compounds in order of increasing boiling points. So you have given some time, try to solve this question and then we will see the answer. Okay, let's see. So for the first part, the open structures of compounds. So if you see this open structure of compound, firstly for the chloromethane, where single chlorine is present at the methyl group. Bromomethane, bromine is present at the methyl group. Diabromomethane, diabromo means 2 bromine are present in the attaching with this 1 carbon. And bromofoam, where 3 bromines are attaching with the 1 carbon. This is bromofoam. So these are the open structures of compound. Okay, you can see we have seen the boiling points order, that with the increasing atomic mass of the halogen, the boiling point will increase, right? Also, if you increase the number of the halogen atom, the boiling point will also increase. So for the alkyl halides which are containing same alkyl groups like chloromethane and bromomethane, the boiling points increases with the increase in the atomic mass of the halogen atom. And atomic mass of bromine is greater than the chlorine, so boiling point of the bromomethane will be higher than the chloromethane. For alkyl halides that are containing same alkyl groups, the boiling point will increase with the increase in the number of halides. If you increase the number of halides, then also the boiling point will increase if you are having the same alkyl group. So boiling point of diabromomethane is higher than that of chloromethane. Okay, and also from bromomethane, because diabromomethane have 2 bromines. Bromomethane have 1 bromine, chloromethane have 1 chlorine of lower atomic mass. So diabromomethane will be having greater boiling point than chloromethane and bromomethane, but the boiling point of diabromomethane will be lower than that of bromofoam, because bromofoam contains 3 bromines. Hence, the given set of compound can be arranged in the order of their increasing boiling point as the highest for bromofoam, then for diabromomethane, then for bromomethane, and then for chloromethane. So this is the order for the boiling points given for the set given in the first part of our question. Now, if we see the second part, we have 1-chloropropane, isopropyl chloride and 1-chlorobutane. So the open structures of these compounds, you can see the open structures, right? This is the isopropyl chloride where chlorine is present at the second carbon. This is 1-chloropropane, where chlorine is present at very first carbon and having 3 carbons in the chain. This is 1-chlorobutane. Chlorine is attached at first carbon and the carbon chain is of 4 carbons. Now, for the alkyl halides that contain same halide, because in these 3 compounds we have same halogens. So the boiling point will increase with the increase in the chain, with the increase in the size of alkyl group, right? So boiling point of 1-chlorobutane, which is this one, which is having the highest chain, the greatest chain or largest chain. So boiling point of 1-chlorobutane is higher than that of isopropyl chloride and 1-chloropropane. Boiling point will decrease with an increase in the branching in the chain. So if you increase the branching, then boiling point will also decrease, right? So boiling point of isopropyl chloride, because at the iso, that means at the second position, there is a chlorine, right? So boiling point of isopropyl chloride is lower than that of chloropropane. Okay, 1-chloropropane. Okay, because there is a branching in the isopropyl chloride than in the 1-chloropropane. 1-chloropropane is a single chain, so it will be having the greater boiling point than the isopropyl chloride. So the given set of compounds that can be arranged in the increasing order of their boiling point as 1-chlorobutane will be having the highest boiling point due to the largest chain, okay, due to the largest chain, largest molecular mass. Then comes the 1-chloropropane, because it is also a chain, but comparatively smaller chain than the 1-chlorobutane. And then there is branch chain isopropyl chloride. So this is the order for the set given in our second part of the question. Okay, let's see the summary. So what we have covered today. First of all, pure alkyl halides are colorless, that we have seen. Volatile halogen compounds have sweet smell. Boiling point, if you talk about, with the increase in the atomic mass of the halogen, the boiling point will also increase. So if you attach the greater or you can say higher halogens present in the higher atomic mass halogen present in the group of halogens with the alkyl group, the atomic mass of the halogen, okay, so with the greater atomic mass of halogen, the boiling point will also be greater or will increase. So the order followed will be alkyl iodide will be having greater boiling point, then alkyl bromide, then alkyl chloride, and then alkyl fluoride. Also the boiling point decrease with the branching of the chain. So this structure, which is having 2 branches, one is for like bromine present as a substituent at second carbon and methyl is present at the second carbon, then this is having the lowest boiling point among the other among these 3 given structures, because this is the most branched structure. And if you see the straight chain structure, it is having the highest boiling point, 375 Kelvin. Then we have talked about the melting point. So para-isomers, they have in the haloarenes, they have more melting point as compared to the ortho and the meta-isomers. Okay, so para-isomers have more melting point than the compared to the ortho and the meta-isomers. You can see that if you see the melting point, the para-isomer is having the greatest melting point, and also the ortho isomer is having the greatest boiling point. Density we have talked about, that is of bromoiodine and polychloro derivatives, the density is higher than the water. Density of some haloalkanes we have seen in this table, that from first to third compound, with the increase of the atomic mass of halogen, the density is increasing, and from 4th to 6th compound, with the increase in the number of halogen atom, the density is increasing. So haloalkanes are slightly soluble in the water. We have also seen the solubility, that haloalkanes are slightly soluble in water, but they are completely soluble in organic solvents due to the energy difference or due to the attraction forces. Strong attraction forces present in water molecule due to hydrogen bonding, and there will be similar attraction forces present in the haloalkanes and the organic solvents, due to which they are completely soluble in organic solvents. Okay. Thank you so much. That's all for today's chemistry session. Thank you.